In this video, I'm going to go over the overall course level learning outcomes or objectives. So what we will be learning at a broad level. We're going to start with a review of probability concepts. Okay, so this part is not in your textbook. So what I have done is I have taken some portions of notes that I have already prepared for a different class, and I have repurposed those content for our class. So these videos and course content will cover probability in depth. We'll start with the classical concepts of probabilities, and then we will look at computing probabilities under different theoretical probability assumptions. Then we will look at events and event probability, conditional probability, and so on and so forth. And then we will also look at Bayes' theorem, which is a very important theorem, especially for data analytics. So at the end of this section, we will have a very good grounding on all the probability concepts that we need for the rest of the class. Okay, because simulation, Monte Carlo simulation, and also discrete event simulation rely very heavily on probability concepts. So that's the reason why we have to go through the review of probability concepts in quite detail. Okay, and then we will look at some basic, simple deterministic models. And again, this is also not in your textbook. And I've taken some concepts from a different class and repurposed it for our class. So which are very small, simple examples. With first we start with the deterministic model, where we don't include any simulation concepts, and then we incorporate simulation concepts into the model using native Excel functions. And then we will also take that native Excel function simulation model and extend it using the at-risk Excel add-in, which we will use for Monte Carlo simulation for the rest of the semester. Okay. And then we start chapter 1. Okay, so in chapter 1, chapter 1 in the textbook actually is only discrete probability, discrete models. So I will have a separate video on that. But as far as course level objectives for the course, for Monte Carlo simulation using at risk, we will be looking at these topics here. So we will go over how to, if you have empirical data from the system, and then we try to fit a probability distribution to the empirical data. So we can then use that probability distribution. So one of the theoretical probability distributions, there are dozens of them under at risk. Okay. We can even, if you don't like any of those dozens of theoretical probability distributions, at risk allows you to set up your own probability distribution, empirical, from the empirical data that closely resembles the empirical data. So we'll look at examples of that as well. And then once you have a probability distribution, and then how do you set that probability distributions up for the uncertain input variables? So you have uncertain input variables like demand or return on investments, change in price over time. How do you incorporate these probability distributions for those uncertain input variables? Okay, so that we'll spend a lot of time on that. Then there is an important concept which is sometimes overlooked, and that is some of the input variables could be correlated with each other. And if we don't consider the correlation between them, we will end up with disastrous results. Like if you have home prices, okay, way back in 2007 when we had the mortgage bubble, okay, one of the reasons for the mortgage, the debacle is that the home prices in different cities were assumed to be completely independent. What happens in Vegas stays in Vegas, I guess. But in fact, they are not completely independent. They are related to one another. So if in one city prices go up, there is a tendency for the home prices in other cities also to go up. So there are some kind of relationship between the input variables. So if we have relationships between input variables, then we need to extract that and incorporate it into the model. And at-risk gives you two ways of doing it. So we have straight correlation matrix, that's Pearson correlation, which assumes linear correlation. And then we have what are called Koppler functions, which are non-linear correlation. So we will look at how to incorporate these kinds of relationships among input variables. Then we will look at running replications of the simulation. So the one main advantage of simulation modeling is that you can run the simulation model repeatedly. So you can run it like 10,000 times or 100,000 times and then see what are the variations in the output result. So if you're looking at profit and what is the minimum profit that we are coming up with, what is the maximum profit, what is the mean profit, what is the 90th percentile of the profit, and so on and so forth. So how do you do all that? Then we can run sensitivity analysis. So if you have decision variables, right? So in the inventory problem, so what should be the reorder point? Should you set the reorder point at 10 or 15 or 20? So you can run the simulation model at different levels of the decision variables and then compare the results. And you can do this sensitivity analysis even for non-decision variable concepts. Like for example, you have probability distribution for uncertain variables. So what happens if you use one probability distribution against another? So, or if you say, let's say normal distribution, if the mean is 100 and standard deviation is 2, what if the standard deviation is 1? What if the standard deviation is 3? And things like that. So we can set the different combinations up and run sensitivity analysis. So we look at that. And then we will also look at how to develop optimal solutions for the Monte Carlo simulation model. So which means if you have different decision variable values, 10, 15, 20, whatever, and you may have more than one decision variable. So you have 10 decision variables, and each decision variable may have 3 or 4 possible alternative values. So if you have 10 and each having 3 alternative values, you're talking about 30 different scenarios. Okay, so now there is a scenario manager that we can use, or we can use optimizer. So there is a risk optimizer that we can use to develop optimal solution under those conditions. And then there is a chapter on how to find simulated forecasts for time series data. Time series data is a particular, is a special case, because time series data is data collected over time. So now, like sales, for example. So you want to forecast what the sales will be next day or next week or next month. And then you may have several products, and some of the demands of these products may be correlated with each other, either positively or negatively, and you want to consider them as a batch and try to forecast for all of those different product lines. So how do we do all that in a simulation setting? So these are the topics that we will be covering in the Monte Carlo simulation as Monte Carlo simulation models. Now, after we are done with Monte Carlo simulation, then we will look at discrete event simulation models, and we will be using the ProModel platform. And it's a ProModel is a object-oriented platform, so it's not sitting on top of Excel like at-risk. At-risk cannot run by itself. At-risk is an add-on to Excel, whereas ProModel is a standalone software platform. So we will look at setting up arrivals and resources and process. Okay, because it is a process simulation, we need to define the flow of process. So we will look at each of those in the ProModel platform. So these are the overall course level coverage for this class.